Okay, so let's start today's session. As we said in the last class, today we are going to go through an example problem from our textbook, that is the optimization of power system operation. So in the last class, actually, we started this article 4.7, and we adopted this method of gradient search technique in economic dispatch. So this was the problem. If we go through a little review of that. So first of all, what we did, uh, the gradient search method, what it does actually, we have to calculate the gradient of the given or the adopted fitness function or objective function. So calculate the gradient. So this was the gradient calculated. And according to this gradient search technique, we have to go against the gradient to find out the minimum, of course. So if we're looking for the minimum, then we have to go against the direction of the gradient. And from that, actually the name comes gradient descent algorithm. So this was the gradient calculated. This is the gradient if the function itself is basically a multivariable function instead of a single variable function. If it is a single variable function, then the same thing is calculated simply by the ordinary differentiation of the function. But if it is a multivariable case, then it becomes the partial derivative n variables. So then the variables of interest, that means the decision variables that we are interested on, that is the unknown variables, are to be updated in an iterative fashion. So the algorithm should start from some initial condition. And let's say this x naught is the vector of the initial unknown variables. Del f is the gradient calculated. And as I said in the last class, I also repeat here that this gradient has to be calculated at a certain operating point. So this del f would be calculated at the previous operating point. That means if I am looking for the value of the x vector at the first iteration, then I know what is x naught. This epsilon was some convergence parameter or the learning rate, whatever you say, and del f has to be calculated at a certain operating point. Means in this case it would be x naught, because we know x naught. We don't yet know what is x1. We are actually looking for x1. So this del f has to be calculated at x naught, where x naught is known. And the generalized case, of course, is mentioned later on. So then we went on for the formulation of the objective function. So because it is the classical economic dispatch, so we are not including the transmission loss. So simply we have to satisfy an equality constraint, that all the summation of all the generation should satisfy the demand exactly. And we are only taking the fuel cost function for all the thermal generating units present in the system. And our target is to minimize that total cost, fuel cost. So because it is a constraint optimization function and we only have the equality constraint to be satisfied, so we can combine these two equations. That means our original fitness function from equation 4.99 and the equality constraint from equation 4.100 with the help of the Lagrange multiplier. So we call this new function as our Lagrangian L, and then we have to calculate the gradient for this Lagrangian. So in total, there were n plus 1 unknown variables, n plus 1 in this manner, that n, this was the number of unknown, let's say, generators, unknown generator real power outputs. And there was a lambda. This is the another unknown. This is the Lagrange multiplier. So in total, we had to play with n plus 1 unknowns. So in these vector of del L, that is the gradient, we will find that there should be n plus 1 entries. So if you count the first one, the topmost one, the first entry of this del L is di L with respect to Pg1 up to di L with respect to Pgn. So up to this point you have n, and then this is the another one. Di L has to be partially differentiated with respect to the lambda. And these are the corresponding calculated values for each of the partial derivatives. So then we have to start the iteration once we know that this is our gradient. So we have to calculate the gradients, and for that we need to initialize our algorithm, gradient descent algorithm. For initialization, what was the criteria that was taken? The simple criteria was that summation of PGI was taken in such a manner that it satisfies the demand. So this was the initial condition. So this was for initial values of PGIs, okay? And lambda naught was calculated as an average value, which is coming up next, how we are going to calculate it. So these are the starting values. The starting values are to be given, or should be taken, should be assumed to start with. So then we will be going through this iteration, and this x naught and x1, all these were discussed. So the generalized updating was done in this manner. Okay. So again, this del L has to be calculated at, if it is xn we are looking for, then del L has to be calculated for x n minus 1. So del L has to be evaluated at all the x values at n minus 1th iteration. So this was the thing that we discussed in the last class, and then there were the steps. We finished with all these steps. So step number, we are going to apply these steps today. So first of all, the step 1, select the starting values of all the generating units in such a manner that their summation satisfies the demand alone. There is no loss. Then step number 2, we have to compute the lambda I for initialization. So the top 0 here is for the initialization. So lambda I 0, the superscript here is basically the iteration number. And the I here is the generating unit number. Okay, so I here goes from 1 up to n, where n is the number of generating units, and the 0 is the iteration number. So you calculate the lambda I for initialization. That means we are calculating the, so there should be D. Okay, that should be D. So dfi over dpgi, where dfi is the only function of pgi. Okay, it is not function of any other I. So once we are taking the fi, it is purely a function of pgi. So that's why it would be dfi over dpgi, and this value has to be calculated at pgi naught, which is known from here, step number 1. Then we have n number of lambdas or lambda 0. That means for n number of generating units, we will be having n number of lambda values for the 0th iteration or for the initial step. So we can calculate the average value of lambda, and that would be our lambda naught. Once you know these n number of PGs as well as the lambda 0, then we are in a position to calculate our gradient del L. So this gradient would be used actually for updating in the next iteration. So we call it del L1. So this would be our del L1. Once we have this del L1, and you see that on the right hand side, all the unknown variables that are coming, those are actually nothing but our x0 vector. Okay, so you see lambda 0 is a part of x0 vector, pg10, pg20, pgn0, pgi, summation of pgi0, all those belong to x0 vector. That means the gradient is actually evaluated at x naught. That's why you see all those knots. So, and consequently, if we say that we are looking for del L2, then what would be the entries? So the entries would be something like this: df1 over pg1, here it would be 1, divided by dpg1 minus lambda. Which lambda should be used here?
Lambda 1.
There should be lambda 1 up to dfn over pgn1, again minus lambda 1. Sorry, not here, it should be from the whole thing. So dpgn minus lambda 1, and this one should be pd minus summation of I equals to 1 up to n pgi 1. So this would be del L2, which is actually calculated at x1. Okay, so in this manner the iteration will continue until the system or the solution has converged. Okay. Okay, so once we have this del L, then this del L would be actually used to update your PG values, okay, in step number 7. But before that, what we would do, we would go through a checking, and that checking is that if all of the delta L entries, or all of the entries, that is n plus 1 entries within this gradient, if all of these entries are very, very small, almost near to 0, in the book they are saying it is exactly 0, but that would take actually a very long time to get converged. So what we will do for running the algorithm, for running the code, we can take that del L is very small. So if instead of taking this, without losing too much accuracy in our calculation, we can say that if del L is less than equal to some, okay, we have already taken some epsilon, so we can, okay, let's say take it as epsilon 1, okay, just to be different than your epsilon of the learning rate or learning parameter. So this epsilon 1 should give you the convergence criteria, and let's take it to be very, very small, okay, or much more small than this, no problem, but not exactly 0. So that means if all the entries of del L are less than or equals to this, then we are done. So one way to do that is to take the absolute value and take the maximum of that. Okay, so if maximum of this del L, absolute value of del L, that means for all the n plus 1 entries, it will check the absolute value and maximum of that. If that maximum value is less than this, then we will say that that is converged, not exactly 0. Okay, so if that condition is true, then the solution would be considered to be converged. Otherwise, we go to the next step, and then we select this scale epsilon for handling the convergence of our algorithm, and this value has to be chosen by the coder, okay, or the solver. So if you are solving the problem, then you have to decide this epsilon, the learning rate or the convergence rate. So step 7, and we said in the last class that you have to choose it very intelligently. Otherwise, if the value is too big, then the solution may diverge. If the value is too small, then it would take very long time to get converged. It will ultimately converge, but the time required for convergence would be pretty large. So the value should be chosen optimally. This is a design, you can consider it to be a design parameter also for optimization, but here they are giving you one value, so you don't have to bother about this. In step 7, so once you get the situation that, well, your del L is not 0 or not less than epsilon 1, not less than epsilon 1, then you choose your epsilon or take the value that is given, and then you compute the new values of all your x entries. Okay, so these are the x entries, n plus 1 entries of unknowns. So these vectors would be updated, and that means now you are in a position to go for your next iteration. So once you know your x1 values, x1 entries, then you can again go back and calculate your this. Okay, that means that would give you del L2, and the algorithm will continue like this. Okay. So now let's go and start example 4.8. So for this, what you have to do, you have to take the data that was given in example 4.4. So you have to scroll up. What is 4.4? Let's see. This is 4.5. Probably this is 4.4. Okay. So these are the values. So this is your F1, F2, and F3. So that means there are 3 units. So the value of n for that example is n equals to 3. Then you have F1, F2, and F3. So this is like alpha plus beta PG1 plus gamma PG1 squared. So let's make it unique for each of the generating units. So this should be gamma 2, beta 2, and alpha 2, alpha 3, beta 3, and gamma 3. Okay. So, so let's list them. So this is my F1. So gamma 1 is 0.0006. Beta 1 is 0.5. Gamma 2 is 0.000005. Beta 2 is 0.6. Gamma 3 is 0007. Beta 3 is 0.4. So these are the values. These are the fuel costs. And although at the starting of the gradient descent, we said that, well, the gradient descent is more likely applicable for the fuel cost functions whose order is more than 2. Okay. But just for example, for the sake of example or for the sake of demonstration, they are still sticking with this quadratic function. Okay. But the applicability for gradient descent, as per their suggestion, is more when we have the fuel cost functions having order higher than 2. Okay. Cubic or more than that. Of course, for quadratic fuel cost function, we know how to solve this problem using the Lagrange multiplier method easily. And that is actually shown in example 4.4. So just for demonstration purpose, they are sticking with the second order quadratic function, second order fuel cost function. And let's start from here. So what is the first step? First step is basically we have to choose the starting values. Okay. So the same data, for example, 4.4, we have taken all the required data and solve for ED with a total load demand of 500 megawatt. So your P demand is 500. So what is the condition? How you are going to start? We are going to start with some values of PGIs such that the summation of PGI 0 becomes equals to P demand. Okay. So in the book, actually, there is some mistakes, probably some printing mistakes or typos, you can say. So the values that are given are actually this or chosen. So this one is correct, but because you can clearly see 300 plus this 2 sums up to 400. So that becomes 700, which is not actually equals to your P demand. So there's a mistake. So just correct it. Just take note of this. So this should be 150. And the second one is actually 100. This one is 250. Okay. This one, third one is correct. So now if you add them, so it is 150 plus 250 is 400, then 100. So that becomes 500. So now it is okay. So you see PG1 summation of PGI. So this equation is actually translated as this. So that is correct now. Then we follow the step where we have to compute the initial lambda I naught for all generators. So what is the definition of lambda I? So lambda I is nothing but dfi over d PGI. Okay. So and then that has to be calculated at x naught. So that means PGI 0. So this is lambda I 0. So now let's calculate lambda 1 0. So this is df1 over dpg1. So if you calculate df1 over dpg1, what was your f1? Remember, what was fi? Fi was alpha I plus beta I pgi plus gamma I pgi squared. Okay. So this was fi. Now, if I'm looking for dfi, so what would be dfi? So dfi, okay, let's make it small because here it is shown as a small. So dfi over dpgi would be what? Quickly. dfi over dpgi, what would be the outcome?
Beta I plus 2 gamma I PGI.
Excellent. So beta I plus 2 gamma I pgi. So that's why you see I didn't actually take note of alpha because we don't need it for the time being. I only took note of gamma and beta for all three units. So dfi over dpgi would be simply beta I plus 2 gamma I pgi. So you see beta I is 0.5, beta 1 is 0.5, 2 gamma I, so that is gamma 1. So 2 into this, so that would become 0.0012. Okay, you multiply this by 2, so you get this. So actually they have written like this: 2 gamma I pgi plus beta I. So this is the pattern they are putting it here, and that is calculated as 0.68, where pgi, that is pg1, should be equal to 150. Okay, so this is 150 megawatts. Then lambda 2 naught, it is same, 2 gamma 2 pg2 plus beta 2. So beta 2 is 0.6, and this is 2 gamma 2, and this is pg2 at initial iteration, pg2 naught. So this is 100. Then lambda 3, similarly, it would be 2 gamma 3 pg3. So pg3 naught is 250, and 2 gamma 3 is 0.0007. So if you multiply it by 2, so it becomes 0.0014 plus beta 3, that is 0.4, and that comes out as 0.75. Okay, clear? Any question? This is still, we are in the not yet first iteration. This is only the initialization going on. So once we have all three lambdas calculated, but we actually need lambda naught, and that is actually the averaged of this. So that means you add this, and this, and divided by n. So that is 3. So you will find that your lambda 0 is simply 0.68 plus 0.70 plus 0.75 divided by n, where n is actually 3 here. So your lambda naught is found to be 0.71. Once you have lambda naught and pgi knots available, then you are in a position to calculate your first gradient, that is del L1. You know the formula, so you simply calculate del L1. So what do we have here in del L1? So in del L1, we have this first entry is df small, df1 by dpg1 0. Okay, so this is 0.68 minus this is lambda naught. Similarly, this is df2 over dpg2 naught, or df2 by dpg2 evaluated at pg2 naught. Okay, that is the correct one, minus 0.71. So 0.71 is this, and then 0.75 is third one, then minus lambda naught. So this is taken from the earlier equation already derived. The last, because there will be n plus 1 entries, so these are the n entries, 3 entries, and the final entry is simply the power balance. So that is nothing but P demand minus summation of I equals 1 to n PGI 0. Okay, PGI for the first iteration. For the first gradient, it would be 0. For the second gradient, L2, this would be PGI1, and so on. So once it is calculated, then you get these vector or this array for del L1. Okay. Once you have del L1, now what you do, you see, you check your condition. What was the condition? The condition given in the book was this, whether del L equals to 0 or not. Okay. So if that is the condition, then you see it is not exactly 0. Okay. Still there are some mismatches present there. So what we have to do, we have to continue. And how? We have to choose an epsilon. So and that epsilon chosen here is 300. That is for handling the convergence rate. Once you choose your epsilon, you have your del L1, you know your PG0. That means now you are actually applying this x of n is equal to x of n minus 1 minus epsilon del L. Okay. So this equation is applied to update these values. So now you know what is xn minus 1 means. Actually here what they are doing, x1, x0 minus epsilon del L1. This is what they are doing. Okay. So they're looking for the first iteration values for all the unknowns, PG11, PG21, PG31, lambda 1. These are x of naught, the first chosen values 150, 100, 250, which sums up to 500, and lambda naught, which was the averaged value calculated here, 0.71. Minus 300, this is your epsilon multiplied by del L1, which is available here. So once you calculate it, you will get something like this. Okay. So that is done. Very simple till now. Okay. So now you have the updated values of your x. Okay. So this is updated value of your x. That means now you have x of 1 available with you. So you know what is your epsilon. This is also known. This is fixed 300. In the last class, I said why we can get away with this fixed value of epsilon in the gradient descent method. We don't have to think about changing or updating this, okay, in throughout the iteration. Fixed value is okay because the gradient itself is changing along with iteration. So the multiplying factor, the multiplied value epsilon multiplied by del L itself is changing. So we don't have to bother about the fixed value of this. Then that means now we have to calculate, we have to know what is del L2. This is what we need to know. Once we know that, then we will be able to find out x2, and that would be x1 minus epsilon by del L2 multiplied by del L. Okay. So now our next step, we know x of 1. So this is my x of 1. I know epsilon. I need to know what is del L2. So now let's calculate del L2. Del L2 would be applying the same formula that is applied over here. So now remember lambda 1 value, which would be needed also. Lambda 1 is remaining at 0.71. Okay, lambda naught was 0.71. Somehow lambda 1 is still 0.71 because actually there was no change. So that's why 0.71 remaining also as 0.71 even in the first iteration after the initial step. So in the next step, we will be calculating del L2. So that means the entries over here in del L2 would be similarly 0.71. So let's go forward. Okay. So this is del L2, and these are nothing but your gamma PG1, gamma PG1 plus beta 1, gamma PG2 plus beta 2, gamma PG3 plus beta 3, minus lambda 1, lambda 1, lambda 1. Okay. And this one is the demand minus the updated PG values. You have to take care of these things. Here you are using updated PG values. PG1, 1. That means this one is the whole thing is actually evaluated at x1. Okay, this is what you have to remember. And x1 is nothing but a vector of size n plus 1. So it is pg1 1, pg2 1, pg3 1, and lambda 1. Okay, so this thing is purely the function of x1. So once you calculate this, then this is the outcome. And again, you check whether del L is equals to 0 or not. So as we check, this is only 0, others are still non-zero. So this condition is not satisfied. So we go and calculate next step, that is x of 2. What is the formula? X of 2 is nothing but x1 minus epsilon into del L2. So we know epsilon, we know x of 1, we know del L2. This is the del L2. So we can plug those values here. And once again, we get the updated values of x. That is pg1 2, pg2 2, pg3 2, and lambda 2. These are the values. Lambda 2 is still, it is 0.71. Still there is no change in lambda. However, other values are changing. PG1, PG2, PG3 are changing. So we continue. Now we know x2. So now we have to calculate the next gradient, that is del L3. And this whole thing would be now function of x2. Function of not x squared, but x2. That means x at iteration number 2. So then once you calculate it, you get, this is your actually new value of the gradient. Okay, now what is coming up next? Actually, this thing, okay, just a minute, this thing, so your del L3, it is again not equals to 0. So what would be the next step? Anyone? Because I will be going to new method now, because they are not going to continue it over here. So what would be your next steps after this del L3? Anyone? After calculating gradient, what we should do? No response. So I should go person by person. Atik.
Yes, sir.
You are there. So what would be the next step?
Sir, is there no solution for this then?
No. What would be your next step? Forget about what they are saying. You checked it, that okay, del L3 is not equals to 0. So what would be your next step? You check that your solution has not converged because all the entries are not zeros. So what you do? So you have to calculate x4, okay, using x3 minus epsilon into del L3.
Oh, I have to repeat the same process again then.
Yes, unless you are converged. You can't stop here. Okay. So
Yes, sir.
if you do this, what you are going to get? Sorry, this is probably, yeah. So this is your PG2. So del L3. Using del L3, we are actually looking for x3. So I did a little mistake. L3 is advanced. So this should be x2 because we know only x2 up to now. And we know del L3. And we are looking for x3. So here they have not shown your x3, but if we calculate it, can we? Because we know x2 is available. We know del L3, we know epsilon. So if it is calculated, then you would get something like this. PG1 3, PG2 3, PG3 3, and lambda 3. I'm not writing down the formula, I'm just writing the answers. 68.45, 7.80, 227.0, and 270.71. So you see your lambda value. What was the immediate previous lambda value?
0.71.
0.71. It was simply a very, very small value. It was manageable. But suddenly we see that this lambda has become 270. Okay. So this is the problem now. The problem is the solution, instead of converging, it has already started to diverge away. Okay. Now, if you don't believe, then what you have to do, you have to continue your iterative process. Okay. So considering this is your x3, then what you have to do, you have to calculate del L4. Okay. Using the same step. And of course, these values. Already it is diverging, what as the book said, because you can clearly see the lambda value, it has a certain big jump over here. It was very small, around 1 or less than 1 throughout the first 2 iterations. In the third iteration, it has suddenly jumped up to 270, which will increase actually as the iteration number goes on. So this is the problem identified at this stage. What could be the remedy? Anyone can come up with any remedy. The book, they have given some remedies by 3 additional methods, but I want to listen from you. Can you suggest any remedy? Of course, I will go through the methods given in the book, but what could be the problem? What could be the problem? We were going nicely, smoothly. Suddenly this happened. And you can see that the lambda value is going very high to up to 270 even. What could be the reason? Any guess?
Sir, epsilon. The value of
Excellent. Epsilon. Excellent. So the value of epsilon, actually you didn't choose it. They actually gave you the value. The epsilon was probably not a bit, it's a very high. Okay. So what I would like you to do, okay, how many of you are here? Probably 5. 1 is absent. Farhad is absent somehow. So what I would like to do, you to test this encoding with different values of epsilon. Okay. And those values, of course, should be less than this, because with this value, it is already diverging away from the solution, from converging point. Okay. So what you would do, take some small value. Probably that would be too small. Okay. But take it and see what happens. If you code it in MATLAB, then you can clearly see what is going on through the iteration. Take the next higher value, 1. I mean, go by, let's say, unit of 10, then let's say 20, then say 50 or 100, or I think up to 100 is more than enough, or 50 would be probably some better value than this. Okay. But I don't know. I didn't check it. But what I see here, they have already taken a very high value of epsilon. So why not choose a very small value of epsilon and try to find out where we have some optimum value of epsilon. Okay. We have good accuracy and we have good speed of convergence. Both is required. Okay, so this is an assignment for you. I will go through the remaining steps, remaining methods that are suggested in the book. But what I would like you to do, to go through a little bit of experimentation, just code it in MATLAB and run for different values of epsilon. Okay, don't take same values everyone. Okay, so if anyone is choosing 0.1, then the next one should choose 0.2, the next one should choose 0.3, so that 5 of you can choose easily 5 values in this range. Okay, for each range, discuss among yourself in the group maybe and choose different values, each of you, so that you can have a nice continuous results. Okay, you get my point? What is your job next?
Yes, sir.
Okay, so that would be nice.
স্যার 5টা ডিফারেন্ট ভ্যালু দিয়ে করতে হবে এটা প্রত্যেকের?
Yeah,
ওকে স্যার।
5 different values from each of this set. That means if one of you take 1, the next one should take 2, next one should take 3, then 4, then 5, then okay, come to 10, 11, 12, 13, 14, like this. Okay, 20, 21, 22, 23, 24.
ওকে স্যার।
It's not a good big deal. I mean, if you just code it, there are only few lines of code is required. And if you face any problem, you can always give me a knock and we can discuss, no problem. But it's not a big deal. It's simply an iterative algorithm. Just play with the epsilon values and see whether you can come up with some solution with different epsilon. Okay, of course, any value higher than these 300 will be also diverging, so there is no point of choosing any higher value than this. Okay, so to get rid of this problem, what they are doing, they are not in the book, they are not actually playing with the epsilon itself, rather they are going for some 3 different methods, and these 3 different methods are little different than each other, and they have shown that with these they have showed that with these different methods, each method has some benefits than the other. Okay, so let's start with the gradient method number 1. In this method, what they will do, they will actually take out the epsilon itself, sorry, the lambda itself out of this gradient calculation. So instead of the number of elements present in this del L, the size of del L would become now n by 1. Clear? Previously, sorry, this del L. Previously, you had del L size n plus 1 by 1. Now in method number 1, what they are suggesting, don't include the lambda part, di L by di lambda part inside this gradient. Instead, simply calculate the remaining n number of entries as it was earlier present. So simply what they are doing, they are calculating di L by di pg1, di L by di pg2 up to di L by di pgn. Clear up to this?
Yes, sir.
So the right hand side would be the same up to the first n number of entries present earlier in the first method, which was diverging. So how would they update the lambda? That is the question. So what they are doing, simply they are making sure that the lambda is also updated, because you have to update it. This is one of the unknowns. So for each iteration, the lambda equals the average of the incremental cost. That means what they did in the first initialization step for lambda, they would do it for each iteration now. Okay, so you see in the first initialization step for the previous example, this was the first initialization step. So what they did, they calculated lambda 1 not, lambda 2 not, lambda 3 not for the first assumed set of values of pg1 not, pg2 not, and pg3 not, right? So they got 3 different lambda values and they took the average for initial value of lambda. But after that, in the previous example, after that, they actually didn't follow these steps for updating lambda. Rather, The lambda was updated through this calculation. You see lambda 1, it is updated with the help of the gradient calculation, because the gradient took care of this additional entry here. But now what they would do in gradient method 1, as by their suggestion, gradient method 1, they would take out this entry from here. So there would be no updating of lambda due to this gradient calculation. But due to this calculation, they will be updating the PGs as before. Okay, PG will be updated, PG11, PG21, PG31. And with these new PGs, they will again go back here and they will put those PGs here. So they will get some new lambdas from compared to the previous iteration, and then they will make it lambda 1. So that means for each iteration in gradient method 1, what they would do, the lambda 1 would be simply again 1/3 of I equals 1, 2, 3. This is actually n, and this is also n in general, and this would be lambda I 1. You get it? Similarly, lambda 2 would be 1/3 I equals 1, 2, 3 lambda I 2 average. That means in each iteration they will take the averaged lambda. Okay, so lambda would be updated following this initial part, not through the gradient. Is it clear? Any question?
Sir, in the first method, then they.
This is the first method actually. This is the first method.
Oh, okay.
This is the first method. I went back just to show you how actually they initialized. Because this loop will continue at each iteration now. Okay, for the, don't call it first method, actually let's call it base method. Okay, this is the base method. Now after that they are calling it method 1, method 2, and method 3. That's why if I say method 1, this one, then it would be confusing. So let's say this is the base method which was diverging. So this was diverging. And how they are trying to get rid of that? Just taking out this entry, not calculating it here. So making the gradient a reduced dimensional vector, and using that del L, updating the PGs. So because there are only 3 entries, now, so you can only update up to PG3, right? You can only update PG3. What about lambda? So lambda would be updated. You have to go back here. Now you know updated PG1, PG2, and PG3. So using that updated information of PG1, PG2, and PG3, you just plug in here, not 150. So you update, let's say for example 159. Okay, this is 103. This is 238. Let's say for example, and now this is lambda 1, 1, lambda 2, 1, lambda 3, 1. So there will be some other values, right? Some different values, 3 different values. So then you calculate lambda 1, that is lambda 1, 1 plus lambda 2, 1 plus lambda 3, 1 divided by 3. You get it now?
Yes, sir.
Okay. And then you continue like this. Okay. So when that is done, so they have given the table, they haven't elaborated everything here because the steps are very, not very difficult, very easy. Just you have to understand where is the change occurring. So this is the method. So they are taking only del L, only n number of entries, and the lambda is updated. You see lambda k, that is k is the iteration number. So where the dfi over dpgi has to be now calculated at dpgik, and then they are dividing it by n. So that is the average lambda. For each iteration, they are calculating the average lambda. Okay, this is what is meant by this 4.108. So they have reworked the example 4.8 for example 4.9. The previous example was 4.8, but still they are sticking with this epsilon equals to 300. So when they go through the iteration, for each iteration up to iteration number 6, they have shown. And what is their comment about this is, you see, now we are not actually calculating this thing. So this is a shortcoming of this method. Okay, in this method we cannot guarantee that p summation of I equals 1 to n pgi equals to p demand. In the previous case we were able to do this. How? Because that equation was actually part of your this gradient. Okay, so here we were checking the condition always whether this del L is 0 or not for convergence, right? This was the p demand minus summation of pgi's, but in this was the base method. But in the method 1, you see, we are nowhere we are actually checking this condition, nowhere in our solution. So it is not guaranteed that you will satisfy this equation or equality constraint. It is not guaranteed. Okay, so this is one of the drawback. The solution will converge, you will get lambda, you will get pg1, pg2, pg3, but there might be some imbalance in the equality constraint. This is the drawback. Is the drawback clear? And why it is coming like this?
Yes, sir.
Okay, so next we go to gradient method 2. So to get to overcome this problem which is faced in method 1, what they would do, the method 2 is a little bit again modified from method 1, but now what they would do, they will add this condition which was missing earlier. So what they would do, they will check that whatever solution is achieved, whether the summation of all those PGs are balanced by the demand or not. Okay, so we need to check the power balance equation for each iteration. That means this is an additional check because we were lacking this checking in gradient method 1. So we need to include that checking here. So what are the checking? There could be only 2 deviation or 2 cases. If you have summation of PGI is equals to P demand, then there is no problem. You accept the solution. Okay, that is clear. The problem will happen either if your summation of all the PGs is greater than PD, or your summation of all the PGs is less than PD, isn't it? This is the imbalance actually. That means they are imbalanced. There is some imbalance. So you have to get rid of this imbalance. How you would get rid of this imbalance? So because we are looking the problem as an optimization problem, so the best way is to follow these 2 things. Okay. The first thing is, if your generation is more than the demand, what you do? If your generation is more than the demand,
It needs to be reduced in the next step.
no, don't go for the next step, because you have to make sure that your power balance is achieved. You can't wait until the next iteration actually. So what you would do, you would select a unit among your available units. You would select a unit among your available units to pick up the power difference. Okay, so that means what? You're looking for a unit with maximum incremental generation. Means, if you remember, in method number 1, you were calculating in each iteration, let's say lambda 1 1, lambda 2 1, and lambda 3 1, right? and then you are making it the averaging of that. So among these three different incremental cost or lambda values, there should be some, of course, some differences among them. Okay, and accordingly there would be some maximum, isn't it, for each iteration. This is for iteration number 1. Similarly for iteration number 2. There would be some maximum. Okay, so maximum incremental cost means what? Is it good or bad as an optimization problem? As an optimization problem, increased cost is good or bad?
Bad.
Increased cost is bad. So what you would do, let's say your demand, let's say for an example, your demand was 500, right? In one of the iteration, you get your PGs like this. PG1 is 150, PG2 is 200, PG3 is how much remains? Another 150 remains. So let's say it is 180. Okay. Now this condition is satisfied or not? You add them, you get how much? 530, isn't it? Which is greater than 500. So that means this condition is satisfied. Now what you have to do? Once this condition is satisfied, you have to check the lambdas for that iteration. So let's say the lambdas for these three are something like this: 0.68, 0.79, 0.61. Okay, I am just putting arbitrary values just to demonstrate the thing, the logic. So these are, let's say, your 3 lambda before you take the average. So what they say? Maximal incremental generation cost. So the maximal incremental generation cost, which one has the maximal generation cost? The second one. So the second one should reduce its output. That means to create a balance, you have to take away how much? Reduce how much? 30, right? So your updated values would be not this array, rather this array. How much you should reduce from the second one? 30. You get it now, the idea? Why are you reducing from the highest incremental generation unit? Because if you can reduce the load from that, you can reduce your cost. Is that clear? Incremental generation means what? Means how much cost is associated or how much cost will be incurred upon you for increasing 1 unit of power output from that unit. So if you can pick up the maximum cost unit, this is your maximum cost unit. That means to increase 1 unit of output power from this second unit, you have to pay $0.79 per hour, let's say, something like this. For the first unit, you only have to pay $0.68 per hour. For the third unit, you have to pay the least. So because you are actually trying to reduce the generation to establish the balance, to establish this balance. Now from where would you reduce? You would reduce from the costliest unit. This is the costliest unit found from this lambda values calculated at that iteration. Am I clear?
Yes, sir.
So you are not going to take 200, rather you are going to take 170 only to make the balance at the same iteration, not in the next iteration. Okay. Okay. Now, if the condition is reversed, what you should do? You have to apply the similar kind of logic, but in the reverse manner. So what should be the reverse manner?
Lambda minimum.
Yeah. So if you have the total generation is less than demand, then you have to choose that unit. Now, because generation is less, so you have to increase the generation, right? Forcefully, you have to increase the generation of any of the units. Which unit you should increase the generation? The least cost unit or the minimal incremental generation cost unit. Is it clear?
Yes, sir.
Yes, sir.
Okay, so I'm not giving you any other numeric values. I hope you can do it on your own now. So these are only some of the expressions which is nothing different than what I said. Okay, so PGS dash means it is the new PGS. That means we were talking about 200, which became 170. So 200 is the old PGS at kth iteration, and 170 is the PGS dash at lambda max. Okay, so this has to be calculated at lambda max, and you are actually reducing PGS k to get PGS prime k or PGS dash k using this formula. If you apply this formula, you will get the similar kind of value that I showed here. Okay. So what were the values? Okay, let's put the values just to be confident about what is going on. So what were the values? Can anyone remember? Oh, 150, right? 200. What was the last one?
180.
180. Okay. So this was these three we only need, and we were playing with this. This was the one we were trying to reduce because the second one was 0.79, probably something like this. Something like this. Okay. So now this is your new one at this specific iteration. K is the iteration number. So I am trying to calculate what would be the new value for 200. So this is my unknown. So it is PGS dash PGS. Let's say this is PG2. This is PG2 because second unit is the maximum unit. And this is, let's say, any iteration K, any arbitrary iteration. So it would be PGS K, which is this one, 200, minus summation of all PGI K. So what is the summation? 530. Okay, this summation. This is what I have got through my iteration. This is the demand minus 500. So how much is this? 200 minus 30 is 170. Okay, this is what I showed earlier. So this formula is actually nothing complex. It's very easy, simple. And similar thing has to be done in 4.110 for the reverse scenario, where if you have got some PGs whose summation is less than your demand, then choose the minimum cost unit and increase its generation. How much you increase, you will find by this formula. Okay, so now because you have updated, something is still left, because you have updated your PGs. Okay, it was this 150, 200 and 180. It was like this. With these you calculated lambdas. Okay, lambda 1 1, lambda 2 1, lambda 3 1. You calculated using these PG values, you calculated lambdas and you found the highest lambda for this case. But as because you are now updating it 150, 170 and 180, so that means you have some new PGs, right? So with this new PG in the same iteration, you actually have to recalculate your average lambda. Is it clear? Because lambda depends on PGs. Lambda value for each of the units depends on PGs. You see, lambda value, average lambda value depends on PGs. So if your PG changes in the same iteration, then lambda must also be updated in the same iteration. Clear? Any question? That means in each iteration, you are actually calculating lambda twice at least. One with the obtained value using the gradient, and then if any of the condition violates, then you are updating your PGs using this formula or this formula, and then you have to recompute the average lambda and then you go for the new iteration. So in this gradient method 2, you will have to calculate lambda twice, unless you have converged your solution, unless you have go to the converged zone. Okay. So this method actually will become clearer only and only if you go through this solution of this method, otherwise not. Okay. If you don't practice, then the method only theoretical talks are not enough. Okay. So please go through this method and try to find out what is actually happening throughout the iteration, how the iterations are progressing, how the lambda values are progressing, and so on. The last gradient method is a little bit a simplified version from method number 2. Here, instead of finding a unit to be the unit whose output is to be updated in each iteration. Okay, here what we are doing, we were in each iteration we were finding this, whether this is true or this is true, and then we were finding whether the lambda, I am looking for maximum lambda or minimum lambda unit. Then depending on that, I have to update the PG for corresponding unit. So in each iteration, probably the PG would be the PG difference would happen for different units. Okay, it might happen. But in gradient method 3, we actually fix a unit to do the job. We don't vary the unit for each iteration. We don't go for this condition anymore. Okay. Rather, what we do a simple trick, and that is we further reduce the dimension of my gradient. So if you have, let's say the previous scenario, how much was the demand? 500. In the previous scenario, what we had 150 and 200. This was the case. Okay. So in the previous one, method 2, we were actually calculating the gradient del L. What was the dimension of that? N by 1. Okay. In the previous method. In gradient method 3, we will further reduce it to n minus 1 by 1. So that means in my gradient, if I have n number of generating units, what I would do, I would calculate die f over die pg1 up to die f over die pg n minus 1. No lambda and 1 unit less. Okay. Not all the units will appear here. One less unit will appear here. Up to this is clear. What would be the dimension of del L here? The dimension would be n minus 1 multiplied by 1. I mean n minus 1 number of rows and 1 column. So if you have 3 units, what would be the dimension of this del L?
2 into 1.
2 by 1. Excellent. So 2 by 1. So that means we will be only updating generations of 2 units. Okay. So how do you get the third unit updating? So that would be taken care of by the slack machine, fixed machine. Okay, let's go through the little theory that is available here. Okay, so the n number of generating unit, if you already know, let's say your first 2 units are generating total 350, and you also know the demand, you can easily calculate PG3, isn't it? This is PG1, this is PG2. You can easily calculate what is your PG3. 500 minus PG1 plus PG2, isn't it? So 500 minus 350, it is going to be 150, and power balance is also satisfied. You get the idea? So you have to sum up from I equals 1 up to not n, from n up to n minus 1. So that is 1 and 2 for a 3-unit system. Demand is as it is 500. So if you know through your gradient calculation how much PG you are getting in each iteration for the n minus 1 number of units, then the nth unit you can easily calculate simply subtracting this summation from the demand, which is done, which is shown over here as an example. So your PGN becomes this, and you can easily now put this PGN expression in your total fuel cost function, function of PG1 plus function of PG2 plus function of nth unit would be, instead of PGN, you can write this PD minus summation of I equals 1 up to n minus 1 PGI. Clear?
Yes, sir.
Okay. So then your gradient calculation will be a little bit modified or updated, a little bit modified. And because why? Because now you have some additional entries here. So your del L, or here they are calling it del F, but it is the same del L actually. Same gradient. I mean, similar gradient calculation is there. So df over dpg1, df over dpg2 up to df over dpg n minus 1. And when you calculate df by dpg1, you see there is pg1 in your first entry of the series, and also there is some pg1 here. Okay. And when you calculate in terms of pg2, the your gradient, the second one will come here, and also there will be some pg2. You get it? And here you have this. The last one will also have n minus 1 pgn minus 1 and dfn pgn by dpgn. So this is actually what we are going to get. N minus 1 entries, but all the entries are now updated. It is not only df1 by dpg1. There is some dfn by dpgn. You see fn is now, or actually pgn is now a function of all the pgis. Okay. So that's why in each case they haven't differentiated it. They have simply written it like dfn, which is a function of pgn, and pgn is a function of actually all the pg1, pg2 up to pgn minus 1. So that's why they are appearing here. Okay. And that will only continue up to pgn minus 1. So you see here it is also pgn minus 1. Okay. So then once you have this, then the gradient iteration will remain as before, and your x is now having a reduced dimension. X is not taking all the n's even. At the base, in the base method, it was up to n plus 1. Then it reduced to n. And now in gradient method 3, it is n minus 1. And this is how gradient method 3 result will come. Okay. So what is the benefit here? The benefit compared to your method 2 is you don't have to actually check the condition every time in each iteration and update the lambda twice. I mean, you have to calculate lambda twice in each iteration in gradient method 2. And here you don't have to do that. Okay. So now the problem is they haven't shown the lambda calculation. So how you are going to calculate the lambda here? Because lambda is not included in X. So remember, the first line says or gives a hint. This method is similar to method 2. So the lambda calculation will be done actually by this. Okay. I mean, you don't have to update lambda because of this. Okay. Lambda has to be calculated only once, and that is the average lambda has to be taken. in each iteration. Okay. So whatever I have said, until and unless you practice it for solving this problem, even by hand calculation, probably you can do that if you are not very much comfortable with the coding. But as an assignment, I would like you to code it, all these three methods, and see how different they are from each other. Okay, and how the solution converges from the starting point. Okay, so this method 1, 2, and 3, you will do it later. But before that, the assignment that I said is actually associated with the base method, but with different epsilon. And gradient method 1, 2, and 3, you have to do it, let's say, for preparation of the exam. Okay, you have the results given, just you have to cross check whether you are getting these values or not. But even I mean, if you are stuck somewhere, then we can discuss with that, no problem. Okay, any question? So in the next class, we will be probably taking another method for solving the economic load dispatch problem. So gradient method is finished here today. So please go through the lecture and try to solve the assignment, as well as try to go through method 1, 2, and 3 besides the base method. Okay, so see you inshallah. And then actually in this
What is the midterm exam date?
Midterm exam will start from 7. Probably you will get a new schedule for your final. Sorry, I mean for your exam. You had a schedule earlier, but probably you will get another request, or I don't know, because the department hasn't said anything about that. But soon you will get your schedule. Okay, or at least you will get a request to fill up the exam dates. The exam will start on 7th of February. That means the next, not this week Monday, the next week Monday. Okay. And of course, you have more freedom to choose the dates compared to the undergraduate students. So I think in the last routine, there were some problems because I think there were exams, consecutive exams, probably those who took the course with Professor Rezaul Haq Khan. So his course students were complaining about the dates. So probably this time around, I will look into the matter, or the department should look into the matter, so that okay, the problem was probably the exam was not on Friday. Okay, the exams for them was not on Friday, and there were high number of students in that course. So probably, and most of them were probably part-timers. So they were complaining that, well, we have to take vacation for that, and not everyone's office allows vacation for exam or part-time MSc. Okay, so 7th, the exam will start, but you may contact whom? You may contact. Okay, I will talk to our department head what should be the policy about your new schedule for the exam. Okay, and because this would be open book, so probably this would be actually online, so I would prefer again to make it open book. Okay, but I will announce it finally before, in the last class before mid, I will actually announce it. Okay, so if you don't have any other question, then we can stop our class here and see you inshallah probably. Okay, probably which day you prefer, Tuesday or Wednesday? Because Friday's class is actually not going to take place. That is the last day before mid. So probably I will get another class before Friday. So which day you would prefer? Tuesday. Okay, Tuesday same time, 8:15.
Yes, okay.
Okay, for all. Okay then. So see you inshallah on Tuesday. Okay. Assalamu alaikum.
Assalamu alaikum.
Wa alaikum assalam.